Yeah, as I told you, now we will restart from the exercise of last time in order to reconsider the fundamental aspect of slide remote control. Of course, in order to understand better this important method, uh, which is extremely important because of its robustness, and I would like to say of its calculation load in terms of application, in terms of, yeah, when we apply the algorithm inside the microcontroller or through the microcontrollers and in robotics and automation, we are speaking about application in this sense. As I told you, it's not a course in slide remote control. It's a selected topic course, let me say related to application distance. Okay, let me open the file of last time. Let me repeat the most important aspects. In the meantime, waiting for MATLAB. Let me open again. Let me show you again the theorem. Probably with the lateral camera is the best way. 1 second. Okay. Couple. Ready. Okay, let me repeat a little bit the second method of Lyapunov, or the second theorem, is, if you like. At the end, I will tell you again in the seminar form of the first and the second theorem, using the material which I used in the course of the lab. I don't know if some of you attended the classes of my lab in which I summarize a little bit two theorems of Lyapunov. But in our course now, extremely important the second theorem, exactly this, because it's, let me say, is more constructive in the sense. If you remember last time, we calculated and now we repeat now quickly, we calculated the control law using just this second method. The first method, or the first theorem, no? Nevertheless, it's constructive, but is more to analyze the structure of the nonlinear system in terms of equilibrium points, also in terms of control, because we can evaluate with the first theorem, nevertheless, how difficult it is to control in some points, to control the system in some points, in some equilibrium points, but in general in some points, or points I intend equilibrium working points or trajectories. Please remember that, as I told you, trajectories are in a set of points. Let me go ahead quickly now because I already told you. The theorem says, consider is positive, just roughly speaking. I have a system, non-linear system, could also linear, could be time invariant. You remember this? Probably I told you a little bit. Anyway, any kind. And a system which can be written in this form as a function of state, the derivative of state, in a function of state, input, and also could change over time. Everything could change over time. Parameters, for instance, we change over time. Think about because of the temperature, which could be not considered as a state. This means the parameter resistance in a coil or in a conductor change over time if in X is not included the temperature as a state. Positive function we will see with an example. In a domain of X. No? Let me say, roughly speaking, in order to clarify, that the domain D is the all possible domain in which we have the definition of X. Anyway, mathematically, we have a domain for the states. Yeah, at a particular point, here is this lecture here is dedicated to a particular system, which I hope to tell you at the end of the course, but I'm not sure. Basically, we have an equilibrium point or a trajectory in which the function, which I define it here, it's zero. This means this is our goal. Probably I will tell you again more effectively later, because he has in a particular application which we can see that it seems that this function here is positive and it's zero for st equal sd, as I told you here before. This is the equilibrium point which we want to consider as our zero, no? Our goal, and I equals zero. We have two variables here, two possible states. It's in a particular application. Very important that I have to find a u v and control, excuse me, is a control law which guarantees the derivative with respect to the time of my initial v function, which must be positive, is negative. And at the equilibrium point, I didn't put here because it's automatically guarantees. I will show you if I choose a suitable way v at the equilibrium point, or at the point which I want to have the equilibrium, the derivative is zero. But let me skip this part here. Let me do the practical example as last time. So we can understand a little bit better. Again, you remember, this is the example of MATLAB, extremely simple. X derivative, x minus x squared plus 2 times u plus a disturbance. Extremely easy example, just one state. Can be written in this form because 0 multiply x. I put here, and a student asked me how I can represent linear system using, do you remember this ABC block, let me say, in MATLAB. I tell you about why this stupid element here. No? Again, this theorem which I told you exactly now in this specific case. Let me consider now more in general in a trajectory, R of t. Do you remember last time we simulate with sine, we can simulate with ramp, we can consider a constant. Anyway, theoretically, any kind of trajectory. Of course, we will see this trajectory must be differentiable. Now we will see. We have these two conditions, positive and including that at the goal should be zero. About the goal, in our case, the goal is x of t equals r of t. Basically, our goal is r of t. Zero is the goal for a mathematician. As I told you, this theorem came from a mathematician. Lyapunov was a mathematician. And then here I have to add, you remember last time I told you that at the goal, when x equals r of t at our zero, the derivative must be zero. This basically sometimes we didn't write, but should be right to be precise. And because if I choose a suitable function v, this is automatic guarantee. I clarify what I intend. One second. What is the meaning, roughly speaking, on this, let me say, four conditions, which basically in the literature are summarized in two conditions, because, yeah, this condition here is in a sub-condition of this one, and this condition here in a sub-condition of this. Anyway, you can formulate as you want also in four conditions, but let me say that this condition here and this condition here, they came, let me say, automatically if I if I define this function in a suitable way. Practically means, look at this picture in which we have here a point in which, let me say, any element, let me figure out in a bar which is here, which is sliding around, through this surface or through this surface, somewhen we will converge here. Think about this. Think about this. Here we cannot see the positiveness. Really, we can also remove the positiveness. If you think at this convexity, if you think. But let me remain in the original formulation. At this point here, we can figure out, we can center somehow this curve at zero, and the derivative also of this curve here at this point is zero. This means just to figure out that this point here is an equilibrium point. The idea is to find an u of t, thanks, let me say, to the second condition, such that a point and a set of points, a trajectory, remember, becomes an equilibrium point or the equilibrium set. Let me do the calculation here, and then I don't have time to demonstrate the theorem, but the application is quite easy. Look at this. Let me consider now again, as I told you, this easy s of t, the error between r of t and x of t. Now, if I consider this v of t 1 divided 2 s squared, of course, the condition one, let me say condition one of the theorem is satisfied, both, because v of s is positive, s is there. We can see that in the formulation which I proposed before, a v is in a function of x it is, because of the presence of this one. This r of t is just there in order to move our goal from 0 to r of t. Because if I don't put here, we have it as x equals 0 is our, let me say, goal, because we have here x squared. Do you remember my introductional lecture? To steer the system to 0. But the 0 is just in the ideal position. In our case, our 0 is x of t equal r of t. Basically, our 0 is r of t. This is totally satisfied. Also, this one is satisfied if you consider that our 0 is r of t. This means s of t equals 0. It means s of t equals 0 means v of t equals 0, but s of t equals 0 means x equals r of t. A trivial. It's more easy to see than to explain with words. Now, let me do the derivative. The derivative of this, easy, no? You are better than me in math. Now, look, from this consideration, this calculation, which is exactly the derivative of v with respect to the time, we can see directly that this is satisfied. Therefore, I told you very often we didn't put this here. No? We didn't put, because if you consider also this easy example, if you put here 0, which means x of t equal r of t, we have it as this derivative at the goal. This is in the mathematical formulation, of course. Is it? This means this is also guaranteed directly from here. But what is the meaning directly from here? Directly from here means directly from the definition of v of t. Going ahead now, we can see how constructive is this condition, because s derivative can be written in this form in accordance with this function here. In this case, s is extremely easy because is just the error. We will see that later we can consider more complex s function. Let me consider d equals 0. Let me consider d equals 0. At the beginning, without disturbance, again, just to understand, u of t is our input, which is the output of our controller, is accessible signal. I can determine, I want to determine u of t to obtain some goals. D of t is disturbance, is not accessible or not accessible directly. An electrical signal which came disturbs the, I don't know, the load in the capacitance. In mechanical system could represent a load. We will see now together as a more concrete example. A disturbance which uh, I cannot filter directly, something which I cannot measure directly. Now, look at this expression here. X dot, it's no, because don't forget that X in the theorem, X in the theorem, f of X is constrained to the system here. Oh, let me consider this. I mean, this theorem here, S is a function of the state, but the state is in a state if I have a system. Do you remember the concept of the energy? Do you remember? In the state, X is in a state if I have a physical system. This is the physical system which we have the characterization of X, which is this one, quite abstract in our case. I don't know, it's a mathematical system, but we will see later more concrete physical system. This means X derivative is this one. Because again, the theorem is related to a physical or at least a mathematical system. If I plug in now this expression here, which came from my physical model, in which I put d of t equals 0, I will obtain this expression. Because instead of minus x of t, I will put x squared plus 2 times u of t. And I have to change the sign. Instead of minus x squared, I have a plus x squared. Instead of plus 2 times u, I have a minus 2 times u. Now, look at this. First step, one method is one method. To calculate an u with the name of it is u equivalent, which realize the derivative equals 0. This is not exactly our goal, because our goal must be negative. But in any case, this is the method. First of all, we obtain 0. We obtain 0 if u of t equals u equivalent equal this one. Basically, putting this part equals 0. This means I will obtain the value of u of t, which I call u equivalent, which is this one. Look, if I put this here, I have here inside 0. Of course, this is not enough to guarantee the stability, because the stability is guaranteed con sufficient condition, please remember, if the derivative of v respect to time is negative. What we can do typically, we add a switching part. In some books we call corrective part, which in our case can be written this form: 1 divided 2, 1 divided 2, beta with beta positive, sg, and sine of s of t. Basically, this u of t, which is the sum of the corrective, the corrective plus the equivalent, which is here. This is the equivalent part plus corrective part. We can see a 1 divided 2 is in both. I sum this here plus this here. 1 divided 2 is I put in evidence. This is the control law. We guarantees, let me go ahead. Exactly this one, because I will cancel everything, but I will remain with this element inside. Again, 1 divided 2 multiply these two elements will cancel this here. And 1 two times, multiply 1 divided 2, multiply this with the minus, guarantees that we have something like that. I don't know if you remember in high school, S of t multiply SGN of S of t is absolute value of S of t. Last time I considered also more in depth this part. Let me see if I find here. If I find, I will show you again. Uh, oh, I didn't find now, but let me see. Last time I told you it's not here. See, oh, let me look. Oh, I don't have here. Um, Let me see if I find quickly. I found probably. Remember this picture here. Sine of omega, sine of S of t, one if the argument is, excuse me, minus one if the argument is negative, zero if the argument is zero, plus one if the argument is positive. Mm. But if I multiply this function by omega t, we have absolute value of omega t. It doesn't matter which kind of argument I have. No? The argument, it doesn't matter what. Multiply SGN of the argument is absolute value of the argument. Probably you know from math. No? I would like to simulate now because this I already told you. I will upload also extra material which is not here, but last time I told you if beta is positive, of course, we have also this. Now, we have the control strategy, which guarantees the sufficient condition for the asymptotic stability of R of t, independently what R of t is. Could be any kind of signal, very important, and a differentiable signal. Should exist the derivative in this sense. Almost everywhere means it could be that in some points uh, it's not differentiable. I don't want to go in depth about that, but nevertheless, thanks to the robustness, we can guarantee that if in some points it's not differentiable, nevertheless we can control the system. But anyway, this is mathematical aspect. Typically, we don't have to do with the function r of t, which are not differentiable. If you think of a robot and trajectories in a robot, yeah, sine, cosine, and so on. What happens if d is not zero? If d is not zero, we don't have problem. You remember I demonstrated last time that it is enough to have beta larger than the maximal value of the disturbance. Of course, I don't know if you remember, typically we have the disturbance and we have also the error in the cancellation. Like case if I find the slide of last time, which is not included here. seconds. Right. Find T. Okay. I is not here. I'm looking for the element of left time backwards. Okay, if I don't find, we go ahead, help to find later. For the Wi-Fi time. This is extremely important concept. Then we simulate. No, I'm not able to find. Uh, but we did together these calculations. You remember? Let me do it for you here again. Let me write. If the cancellation is not perfect, this means here inside we have an error which depends. What is the meaning of the cancellation? This part here realizing the cancellations because I will cancel this part here with minus because of this minus here, excuse me, because let me see, where is, yeah, here, excuse me. Because of this minus 2, I will cancel these two elements if I know exactly R of t, I know exactly, but the coefficient which we have here, in the model we have a 1 multiplied squared, but I'm not sure if you have a 1. Could be also 1, 1, 1, 2 in real case. This means the cancellation is not exactly perfect. This means we can consider delta. Let me say, do you remember this concept of delta max, which is the maximal error in the cancellation, plus d of t, which remains here. Do you remember? I told you this is the what remains after the cancellation. This is extremely important. But nevertheless, you remember, if I divided everything by b, I can write in the sense, put in evidence in the sense. If I put in evidence, let me write, otherwise it's too, error in the cancellation, the error in the cancellation. Then we maximize a little bit later. Do you agree? Excuse me, here is the error in the cancellation, is d of t. Now look, this is less or equals what? Less of equals s of t b or beta, as in, it doesn't matter the name. Very important positive. No? Look, now, the upper bound. Uh, typically, we consider also in this form. Because of course it's the most difficult point. This negative is, helps. Helps because we have to demonstrate that for each delta is negative. But if less or equal 0, or better to say less than 0, now I will show if beta is larger than this. You remember last time I demonstrated. Now I will go ahead quickly, but it's intuitive. No? The demonstration last time I invested time because basically this element here with this condition is still, is always, I would like to say, less than 1 in positive. Clear, no? This means depending on the sign of ST, this is always negative. Why that? Because if S of t is positive, this element here is -1. You remember? It's -1. But as I told you, this is less than 1. This means the contribution of here inside is negative, remember? But I told you that S of t is positive, beta is positive, this means it's negative. If, now I don't write, but last time you can find in YouTube, but if I find the slide, I will upload. But it's easy. If S of t is negative, this here is -1, with minus is +1. Yeah, you see it. If this is negative, this is +1. This in any case is positive. Because this is positive. Remember this, even though less than 1, but it's positive. But this is negative. This means remain negative. Easy to see. Very interesting, the last things, and then we will go ahead together with the simulation because it's more interesting to understand that on the surface, we are insensible with respect to the disturbance. If you consider just the disturbance, but you can also here add all kind of uncertainty which I have, because the corrective part compensates directly the disturbance. This is an important concept. I don't have time to go in depth, but probably you will work on this in your thesis and so on. Please pay attention. When we are on the surface, exactly in this situation here, which I am sliding, I am on the surface. Yeah, I can remain on the surface, ideally, and if I, because of this of this control action, which guarantees that I remain on the surface, at least mathematically. Why that? Because I realize, let me see in order to with this control law, I guarantee that S derivative is equal 0. S derivative is equal 0. Thanks this part here. This means I will remain on this. But to guarantee that I remain, I need this because this guarantees the attractiveness, the negativeness. This means as long as I am on the surface, it's a mathematical concept. I will compensate everything which disturb me from the surface, in the sense. Remember last time I showed you also this picture here In the sense, I can consider so any kind of set of points, the trajectory. Of course, in this sense, you can imagine in a surface, I realize in a manifold, let me say, centered on this trajectory. It doesn't matter which point I am, I will converge here, and then I will stay thanks to the control law. Look here. U equivalent guarantees that S dot equals zero. If I go out, I have the switching part, which guarantees that I come back to the surface. When I go out, for if I have a disturbance, this means totally theoretically, the corrective part guarantees that the system is unsensible with respect to the disturbance. Because I reject the disturbance thanks to the switching. A little bit the complex concept, of course, but at least I told you a little bit. Okay, let me now simulate a little bit. Probably is easy to show you the simulation to tell you about this concept instead of tell you mathematically. But anyway, let me open the file. Okay, here. No, I didn't put probably. Okay, just 1 second. I look in another folder. Oh, I put it. I don't remember. As another 1 second. I copy. I put there. So okay, 1 second again. Okay, slided example is exactly what I upload in our electronic campus. No? I am opening the file. Okay, let me share now. I hope it is working. Ah, you remember this. Now you have also, let me show you. Hmm. Uh, Remember last time, this is the system. Now we can, if I go inside, we can understand the concept why I put 0 multiply x. This is 0, no? Because we don't have a linear part. This is a little bit the answer. B, we can see that consists of 3 elements. 2 comma 1 is exactly a little bit the concept to realize the wrong cancellation, no? Because we thought that the coefficient was 2. In our model, the coefficient was 2, but really in the real system is 2 comma 1. But the control is so robust if beta is large enough, which overcome the error in term of uh, cancellation. No? And then minus 1 and 1 here and B, I put it, let me say, uh, without error in a sense. No? This minus 1 reflects this minus x squared, and this 1 is the coefficient, let me say, I don't want to say of the disturbance, but the coefficient of the system with which the disturbance will go inside. If you want, you can consider also the coefficient of the disturbance, but it's not exactly correct because it's the element through this element the disturbance go inside the system to the system. D, the matrix D consists of 3 column and 1 row because D, I don't know if you remember what I told you, or probably you know from other courses, D the same number of row at C, the same number of column as B. If you look here at the definition of the structure of the linear system in this frame, the frame A, B, C, D matrix. Do you remember? We did a lot about that in the first part of the course dedicated at these selected aspects of the linear control systems. Yeah, the second element, as I told you, is minus 1, which is multiply, we can see here, x squared, uh, multiply minus 1. If you remember, this element is going through B to realize minus a squared. This is in a constant disturbance. Let me consider here as the input uh, something easier now. It's in a constant, for instance. This here. No? And this is the control, which I told you last time. Let me now show you a little bit the robustness. You have the disturbance equal 1. This means the corrective part here, we let me write here also here inside instead of 2 comma 1 just 2, just to show you the robustness. Look, if I put here a value 2, you remember this is beta. I should guarantee the stability. Stability means asymptotic stability. This means I will converge to 99. Let me show. Because 2 is larger than 1. We have just one disturbance. Here I have to connect, excuse me, to compare. 1 second. One second, because I don't understand what happens here now. Okay. I have to connect, as I told you, this is the goal, 99. Um, Let me check again here. Yes. Let me check in order to show you what I am doing. Look here. Here we have the approximation of the SGN. Do you remember last time I told you? Using this case, 2 divided by arctangent, which is a sigmoid function. This coefficient here inside allows to approximate better and better this ideal sigmoid function. I don't know if it's important to show you a little bit what I intend. No? 1 second. Exactly this case here. You can use the hyperbolic tangent because it could happen that this SGN can generate problem because it's not in a continuous function. And that's also in the implementation microcontroller. Very often we prefer to use an approximation of it. But if you look, the approximation is better and better if I consider larger and larger gamma. We can see here gamma 1 larger than gamma 2, the red color, which represent the function with gamma 1, approximates better this SGN, just to understand why I am including this. Um, it seems from here that this exactly represents the uh, our beta, excuse me. Okay, let me run. Should be stable because it's larger than 1. The amplitude of the unique uncertainty, the disturbance, is 1. Let me see. Yeah, this is a little bit results. Let me show you. Now, I don't understand why it's so disturbed. Probably, I don't know if I added some noise. Should slowly converge. Let me see if I have some other errors which I forgot to cancel. Let me see. Here inside, one thing. No, is okay. Mm, I cannot justify. Uh, Probably. Let me see here. U is quite disturbed. I try to reduce this element inside the arctangent. It could be that numerically we have some problems. Let me see now. It seems to be not better. Let me see the calculation 1 second. Mhm. It's not better. Let me disconnect this. It's not better. I don't understand. Okay, let me see. Let me see here inside. Um, the technique which I used to simulate. Could be that some student ask me some question. It's strange how it's so disturbed. No, it's correct. Everything is the method which I simulate is. Let me increase a little bit. I don't understand really why there is something wrong, but I'm not able to see immediately. Probably I changed something and then I mean now we can see the convergence I show you, but why it is so disturbed? It's not so much disturbed. I show you what I intend. Probably okay, okay. Now I understand. 1 second. Yes, probably too long. This window, therefore, is not so. Even though I don't like the simulation exactly. Now we will analyze together. We have something like that. We can see the convergence starting from initial condition 100. Yeah, we can see I will convert to 99 relatively quickly. Uh, but in my opinion, it's a little bit strange. This signal, let me look how I can improve now. I increase gamma inside the arcotangent. No, we can see a little bit the results, even though I don't like this stark chattering. It could be probably improved using a different sigmoid function. Let me clarify what I intend. Here inside, for instance, I tested, to remember this. This was an approximation of the SGN as a saturation function. Basically, inside phi, which can define as I want, we have basically a linear function. And outside the sign, let me show you if this can improve. In order to have also this concept. Oh, I don't think so that improval could be that I have to increase this. But 10 or minus 6 is really extremely small. This is the results. It's not much better. Let me try mathematically. What happens with this Gn? Okay, Sgn of S. Let me show you again. Now I am considering Sgn of S of t mathematically. It could be that doesn't work, huh? Because not necessarily MATLAB is able to work with this Sgn. Let me see. It's not bad until now. Yeah, this is the best result. Basically, if his work is always the best results, because we demonstrated everything without approximations. And of course, nevertheless, practical application, it could happen that for complex control law is not so easy to yeah, of course, numerically with SGN, but we can see that it 10 up to -3 the error, the maximal error. Now, what I want to show you, and then we will conclude with this. If we have to overcome an uncertainty is equal 1, is here enough as a beta to put, I don't know, 1 comma 1, 1 plus epsilon mathematically. Let me show you what now I put 1 comma 1. Of course, I will converge, but very slowly. I show you now. But I will converge. Now, let me write 0 comma 0,9. If I put 0 comma 0,9, we will see that we have some problems. Let me go. Just to emphasize some important aspect here. Let me write here 0 comma 0,9. No. We waiting something unstable. Let me run slowly, but unstable. In order to show you the concept of beta, should overcome what I don't know. Uh, okay, let me now put the stability. Let me the factor 2. I put factor 2. Let me show you with the factor 2. We will converge a little bit. We need more time, of course. Converge. Oh, no. Quite so strange, the signal, what I did. I don't know what I did. I changed something. Before was better there. Did you see it? I changed something in Simulink, but I don't remember what. Let me see. Uh, what I changed. Anyway, and now I don't know, but conceptually, that is strange because I'm not able to reproduce the results. Probably I changed and I'm looking for what I changed. But we have seen that we had result before. Clearly, excuse me. I'm stupid because look, the reason is that I connected again the approximation. This means to obtain good result, I have to put large gamma here inside the argument of arcotangent. But it could generate also some numerical problems. With 1 comma 1, we have the convergence, even though relative slow, no? Because we overcome, but no, relative slow. Let me put in a large value, I don't know, 5. We can see that we will achieve now with beta equals 5. Yeah, we can see here. What I do? Why? We have an error now in Simulink. Yeah, look in Simulink what we have now. Let me show you. Zero crossing means this switching, multiple zero crossing. This means we have to be able to disable this. Otherwise, yeah, fix. No? Otherwise, practically, if I fix, I have the system approximates internally this SGN again because in very small interval or the regions you have to switch theoretically around zero is if I oscillate around zero we switch between one is minus one and the system could have problems in this oscillation. If I fix it generates in a tolerance region. Now let me show the results. If I fix now, let me go. I This is something again wrong. I don't know what I changed, excuse me, really, for this problem MATLAB. Here's not the problem. I don't know what I changed now. But we have seen that somehow it works. Let me see now. MATLAB is. Hmm. Now again, we have some problem of switching. You can see it's blocked. Yeah, you can see it is blocked. Okay, to conclude, probably the best way is to put here an approximation. Let me see if I put here an hyperbolic tangent that typically is most robust. Let me go here inside. Let me write. Hyperbolic tangent is, I don't know, I don't remember the command. Let me see. MATLAB. Look for hyperbolic tangent. Let me see. I don't remember the name of the function. Okay, if I don't remember, I have to look here probably in Simulink. The name, how I can call the hyperbolic tangent. Let me see. Understand anything here? This one here. Okay, library, math operation. Exactly. Let me look here. I don't see any hyperbolic tangent. Huh? I don't see anyone. Strange. Okay, let me look somewhere. Let me see. Tan H. Okay. This means let me go here now together with you. Tan H. Then I put in the gamma, I don't know, 200 multiply U, the argument. Okay, let me see now if I have some better result. Typically is more robust. Not really in this case. Try interesting. Why this? Mm. Let me see. Starting from here, it seems to be not bad, but really I don't understand this effect here. Could be that in the file we have something wrong. Okay, the last. Um, Last thing which I want to tell you, let me see if I find the possibility to do it. Otherwise, we take a rest. I will try to fix this aspect here. With similar matter, but I will present in a new case after take a rest now. Let me introduce there's another exercise. This should be, in my opinion, more interesting. It could be that you have some numerical problem there due, I don't know, probably the approximation of the system to. Anyway, look at this example which I want to present as a real example could help also in the concept of the examination of the project. Let me show you in the lateral account that we take a rest. I try nevertheless to fix this problem here. I will scan this and I will upload it directly now because this is a little bit the system with a possible scheme of such kind of problem. I worked with MAN, the company which build Lorry to stabilize or to minimize oscillation of the this drive position, let me say, or driver position. We can model in this form. It could be that this example, it's a shame I don't have real value, because with the real value I don't have here. Can help also to minimize this well, sometimes this numerical strange effects. Anyway, we will see together the model. We will see together in the constant of uh, sliding mode. I hope to find also, otherwise we calculate, I have it. You can see here the calculation from the sliding, and then we will try to implement at least, let me see, until here we have the problem a little bit more complicated, but we will try to implement until here. Then of course here we have the demonstration, and this, excuse me, this part here until here we try to implement. Here is the proper formulation for an exercise of the bachelor thesis. This means this part here we will not consider. Okay, let me try to fix up this problem which we had the simulation. I will scan this and will upload this in a possible exam exercise in order to understand the structure. I think here is still interesting, nevertheless, because it's not so interesting in the sense we can see again everything which I told you, and then after explain this and implement it, I don't have the implementation. This means we will do together. Could be helpful. So could help. Could be helpful. And then we will go ahead with some particular aspect of the sliding. We stop, let me say, 50 minutes, 20 minutes, not more. 3 o'clock we will restart. We will see in 15, 20 minutes, more or less. See you later.
See you.
Okay, let me go ahead with a more realistic example. Probably we will reduce these numerical problems for two reasons. One is, I would like to say, more realistical example can be better modeled in the sense, even though I don't have exactly the values, but I can, let me see a little bit to figure out in accordance with my experience. But moreover, we will see as more realistic, more suitable, I would like to say, S of t, surface. You remember, surface, or the sliding surface. The word sliding now make more sense in this example, because do you remember the function which I use until now? Let me show you again. Was the error. It's not so exactly in the sliding function, and there this can generate this fault, this switch, which we have seen, and then I will come back on this, but let me show you the idea why we cannot speak about the sliding, and this can generate problems, because this S of t, which is our error, exactly the error, when S is 0, we are already at the goal. This means S0 means x equal error of t. This means, do you remember my first lecture, as I told you, we achieve the sliding surface in infinite time, and then we will slip or we achieve the goal in infinite time in our approach. Now, if we are considering just this surface, or this surface, which is exactly the error, the sliding mode, let me say dynamics, finished exactly at the surface. This means we don't have this switching, excuse me, this sliding phase. This means the switching acting directly on the goal, and basically we have let me say, a direct effect between disturbance and switching. This means can generate exactly these spikes which we have seen, because we don't have the dynamics on the S equals 0. Now we will understand a little bit and understand a little bit better when we analyze exactly the mechanical system, which is a little bit more realistic, also in the context of, let me see, of the surface. Let me go ahead with this. Yeah, we have the system here. The idea is to control the oscillation of the driver, consider it as a unique mass. Of course, I worked on this real problem when I was young. The model of the seat of this lorry, as it was in lorry, MAN is in a company which is building also now it built lorry, track to let me say reduce the oscillation at the level of the head of the driver. But of course, the complex model should consider also the vertebral column of the driver. It's extremely complicated in any case, but also boring to tell you about that in the basic lecture. It's basically in the project, a master thesis or PhD program. But in any case, considering here just one mass, this is easy. This is more realistic than the mass, to consider the mass of the driver. The problem is, in this case, to control, to minimize the oscillation of the, let me say, of the driver, when some disturbance occurs, from the road directly. Of course, here we don't have the model of the wheel, we don't have the model between lorry and the wheel, that we have just this system here. Nevertheless, it's not so bad, because we can consider from here some disturbances which came through the wheels, through let me say the chassis of the lorry. We can schematically consider the system here in this form here, which we have. We can see a spring system and damping system, exactly what we have typically in a car, for instance, in an automotive system. Passively. Basically, our damping, our amortizators are realized by a system which consists physically by spring effect with its stiffness, and then the damping effect. But of course, in our case, in which we want to try to limit all the oscillation also actively, we can consider an input as, for instance, an hydraulic system activated by a pump. Here, of course, is everything schematically represented, because otherwise the system is really in a PhD program. No? Yeah, we can see here D of T, the disturbance. The disturbance which we can consider, for instance, here directly on the mass. Of course, we can also model the system is in a different way. For instance, the disturbance we came from here. a little bit more complex, but not so extremely much complex. I mean, try to think that I am traveling in this direction. When I have the bumps, we can consider that this position will change. If you want, I can show you what is the difference between the model with the disturbance of the model with the disturbance, the model of the disturbance which came from here, and the disturbance which is directly on the mass. Yeah, it's a little bit simplified because we are here to learn. But here, if I put the disturbance here, of course, it's more realistic in the sense that the disturbance came somehow. Of course, it's not directly correct because, yeah, it's in the scheme, because we don't have the wheels here, we don't have the chassis of the lorry. But of course, if I model somehow the disturbance, or if I consider, because it's not exactly a model, the model is the whole system. If I consider disturbance which came from this profile, it's a little bit more realistic that the disturbance came from directly, or is directly on acting on the mass. But let me do that, and then I tell you what changes here. Okay, let me consider again the positive direction x of t. If you consider up, I consider also the positive direction of the force. The force here is the force which is generated by the hydraulic system through the pump. Of course, the hydraulic circuit is, is complex a little bit, but let me realize in a scheme of this in order to go ahead with the knowledge which we have in this course. We want to realize a system and a control system for this mechanical system which compensate, we reduce, better to say, which is robust with respect to the disturbance. If you want to use the word of the sliding mode control, which is unsensible, or at least mathematically unsensible with respect to disturbance, independent of the disturbance is directly modeled on the mass, or more realistically, the disturbance is localized, let me say, at this position. We will see a little bit the difference in between. We have the mass, concentrated, you remember the word of concentrated, what is the meaning? Ks is the spring factor, stiffness of my damping system. Kf is the friction factor, which is a part of the damping system. I told you about that. F of t again is the input. Look at this now. Look at this equation. If the disturbance is acting direct, we think acting directly on the mass, this is the model in which we can see that the disturbance is at the level of the force. We can see the input force. I can do that in the system here thanks to this f of t. Thanks to this f of t. F of t is the output of the controller. Now we will design the controller such that I theoretically, mathematically, on the surface, do you remember? On the surface, I realize a system which is not sensible with respect to the disturbance. Mathematically, I will cancel the disturbance, of course. We are not really working, I mean, at the beginning, we are working mathematically, but then we will approximate somehow to realize it. Do you remember this SGN? SGN, it is impossible to realize exactly as a mathematical function, because this means it's in an infinitely small region. I will change between -1 and 1, not only. Practically, I will change between minus beta and beta. Beta could be also very large. Remember, because must compensate what I don't know. This means practically it's impossible. Therefore, we approximate with other sigmoid functions. Remember, hyperbolic tangent, arcotangent, or different, also other functions. Anyway, it's clear that if you look at the picture, that if the disturbance is considered acting directly on the mass, f of t and d of t they are acting at the same level. The same level means they are algebraically, let me say, directly connected. The difference is this is the motoric force, the output of the controller, which can be realized with the pump, the hydraulic system, pneumatic system, different form. This is not directly accessible, but indirectly can be compensated. You remember the concept of the I have to reach the surface as soon as possible, as soon as possible. About this, as soon as possible, at the end, I will tell you something which I didn't tell you until now, huh? Because I am proceeding slowly and slowly. Huh? Why this balance here? Because the inertia, the mass multiply the second derivative of x plus kf1 multiply x1 derivative plus kf0 multiply sgn of the derivative of the velocity. Again, the same argument. No? This is the friction force in accordance with the Coulomb. Do you remember I told you this? The Coulomb model of the friction. Basically, the Coulomb model realizes realizes the friction as a polynomial function. No? Here we have a constant. Of course, SGN is there in order to express the concept that is always against, let me see, the velocity. Against means, think about these two elements here on the other side. Against of the force. No? Better to say against of the velocity. But if you put in the other part, we can see better the Newton law. Inertia equals motoric force, disturbances, minus friction forces minus spring force. I told you about that. Exactly here. Yeah, I am considering just three because I didn't consider the disturbance. No? 1, 2, and 3. Of course, if I consider disturbance, I have to put 4. If you want, I can correct, but it's not wrong. Very important to clarify. The clarification basically is here. No? But of course, here we have also as an effort. But why we did include, because this is more technical. Could be there, could not be there, could be 0, therefore. During the travel, this could be, of course, 0. But anyway, I can include 2. It's not this is the problem. About that, I already told you how we can approximate this ideal model using, it doesn't matter which kind of sigmoid function. I told you a lot of time. Interesting that this function here is present in the model, but it's present also in the control law. Again, hyperbolic tangent, 2 divided p tangent. I don't want to spend energy to clarify again this. No, gamma positive, larger and larger gamma, better and better in the sense we approximate SGN, let me say it better. The advantage of this approximation that the function realized by or the using this hyperbolic function or arcotangent function, they are continuous. Lyapunov control strategy. Now we are able to do that. We have a system, the dynamics of the system, which in our case, please pay attention here, 1 minute, is this one. Again, excuse me, I didn't consider this disturbance. I will consider later. This is also in a normal, some authors, me too, at the beginning, I don't consider d of t. Therefore, I told you, typically we put just, this balance without the disturbance. But of course, at the end, if the disturbance is present, typically yes, we increase this balance here, even though at the beginning I didn't consider. It's the same concept here. No? if you look here, in this representation, basically is the same here. No? I don't know why I repeat it. Yeah, just to put some notation probably, because I don't see any difference. Yeah, let me consider directly this. I didn't put any disturbances, of course. We can consider later. This representation here we have seen in a different context or something similar. Basically, we have the vector of the state x, which consists of position and velocity. x1 is the position and x2 is the velocity. We can see from here the derivative of the position equals the velocity. And the last equation represent, if I consider multiply by m here, mx2 dot is the inertia because x2 is the velocity, because it's the derivative of x1. x1 is the position. Do you remember? I explained very quickly, but we have seen this kind of system. Do you remember when we have seen at the beginning of the course the car, when we have seen the aerostat system? X is written nevertheless here. X is the position. This means x derivative is the velocity. If I call now x equal x1, x1 is the position. x1 derivative is the velocity. Exactly what I'm writing here. No? Now, this element here is not a matrix anymore because the system is not linear. We don't, well, okay, we can also represent in matrices or pseudo matrices, even though it's not typical. Typically, we consider this vector here. We can see an element here, in a scalar here, x2, the velocity, and also this expression in a scalar. This f of x, the name is field. Probably you remember from math or analysis 2 or something like that. And of course, we have also this input field, let me say g of x, which in this case is a vector because we don't have any function of the states here. But could happen. In general, we find in the letter g of x is the input field because it's multiplied by the input. Yes, fields. As a representation, independently of the nomenclature. But of course, think about that this is a scalar, this is a scalar. No? Here also the same. In our case, we can speak about that the g of x does not depend on x. Lyapunov theorem. Again, now we are able to work with this. Positive. I have to choose a positive function in accordance with the theory. At the goal, we didn't fix here the goal, must be 0. And the derivative with respect to the time of this function, which depends of x1 and x2, must be negative, and then this one, here I put it. Basically, we have to find an f of t which stabilizes the system asymptotically. This means exactly, I didn't tell you extremely in detail mathematically. I mean, I didn't show you the demonstration. This is the meaning of this asymptotical stability because we will converge to 0. And when we are at 0, it's not the explicit visible. We will stay at 0, but asymptotically. Here is the theorem is just sketched. Of course, we have also finite time methods or control law. I don't have time to tell you. It could be that I will sketch something in order to show you that not necessarily we are limited to work asymptotically. Asymptotically means we need infinite time to achieve the goal. as I told you, is not a big limitation because practically, this is a problem mm, of the model. I mean, we will see that if you are using this model here, we have let me say a point, a time in which we will stop infinite time, because when we are not able to overcome the static force, we can see here the static force, we will stop. This means this analysis, even though it's asymptotical, is an asymptotical analysis, nevertheless works in finite time because of the presence of this. Okay, I hope that I didn't forget anything. Okay, we can go ahead. Let me show you now the control law. V of S of t, 1 divided S squared. Easy, extremely abstract. Because what is S of t? Look at this function here. S of t is, now we justify the choice, no? The error with respect to the velocity, desired velocity, plus k multiply the error with respect to the desired position. It's a standard Lyapunov function. K is positive. Do you remember I told you last time about k? I think I hope that we discussed together about k. Anyway, we can discuss also now. No problems. Why this choice? First of all, I have to say that we have a system of the second order. We have, the second order is not correct. System with two states. This means we have also an interesting criterion which can be also demonstrated to choose the let me say the surface. The surface, the order of the surface is basically n minus 1. Now we will see why, which n is the number of states. This means the order here is 1, because we can see that the derivative of the first order is basically here. We can see, we consider both. No? But here we have the derivative of x1 plus k multiplied the error. Before, we had a system of order with just one state. This means 1 minus 1, 0. No? Again, the order of the surface is calculated n minus 1. The reason is a little bit, let me say, it's not so difficult theoretical to explain. Practically means that I try to reduce the order of the system on the surface because I have to be able to include in the control law the input u. This means it depends on the order of the system which kind of surface I have to consider. Let me a little bit go ahead and then we will reconsider this sentence here. Very important, nevertheless, to understand that when s of t is equal 0, when s of t is equal 0, we have the dynamics. I mean, I am going to 0 for the error of x1 with this dynamics, the error derivative plus k multiply the error. This means increasing k, I will speed up. Do you remember this we have seen at the beginning? The error which is going to 0. Now we will come back on the concept of n minus 1, because it depends of the relative degrees. Probably I don't know if you heard about relative degrees of the system. I show you practically. Derivative. We have seen many times. For s equals 0, when we are on the surface, we have that v derivative is equal to 0, as I told you. Now, if I do s derivative, which is written basically indirectly here, I have to do the derivative of this, we have this. Basically, I realize the derivative of this one, which we have x1 dot dot plus x1d dot dot plus k multiply the derivative of this one, which is x2 minus x2 desired. x1d, before we have x2d, x1d is the desired state 2 and the desired state 1. No? The desired state 2 and the desired state 1. Our goal. Now we can understand why I am considering intuitively this kind of surface. We can understand because from here I can have the input f of t, which guarantees that s dot is equal to 0. Because if I replace this element here with the model, which is here, x1 dot dot equals x2 dot. But x2 dot, we know, x2 dot is this expression. Now we can see that I include in the surface s of t, f of t. This is our goal. Therefore, I need for a given Lyapunov function candidate, which includes all states, x1 and x2, and the surface with the order, let me say, n minus 1. N is the number of the states, 2, n equal to minus 1, the order of a surface is an order 1. You can see from this derivative. Because this is enough to do the derivative of f of t with respect to the time to have inside the s derivative the input f of t. Let me see if I can improve my explanation. Because the relative degrees between, let me say, x1 and f of t, or vice versa, is 1. Is 2, excuse me. Is 1. Is 1, excuse me. Therefore, I need the surface order 1. Because we can see from here, if I do the derivative of s of t, I have inside f of t, which can realize this concept of s1 s dot equals 0. Because I can choose f of t such that this element is equal to 0. Remember, with this equivalent part. Let me see if I can improve a little bit the concept. Let me see if I can improve here. Yeah, I see an error. Yeah, excuse me. Yeah, I see an error at zero, no? Mm. Excuse me for this error. I will scan again. I will upload. Yeah, I don't know why it is I put one. It's definitely a zero. The reason is the derivative of x1 equal x2. No forces here. Should be nice, easy to control. I don't know if I mean in both cases no sense. At least in this case, no sense. Let me see if I can. Mhm. Yeah, this is zero, because otherwise no sense, because the derivative, the position equals the velocity. The force doesn't make sense. Excuse me for the error. I will scan again. Um, because with one derivative, I will obtain f of t inside of s dot t. And then inside s dot means I can impose the invariance of this sliding surface. S dot equals zero means invariant s of t. Basically, I remain of s of t equals zero, excuse me. Is here. With this f of t, I guarantees, at least mathematically, once, please pay attention, when I have on the surface, I will remain there. Once I have on the surface, mathematically. Why that? Because this expression here, if I, without this, the equivalent part is good written. The equivalent part guarantees, if I put here, that I will cancel here. I don't know if it's correct. Let me see. Yes. No, it's not totally correct, no? Because I have to add. It's not totally correct. I forgot something. That is compensated. This is compensated. This is compensated. This is compensated. But I have to add this and this. Excuse me for the error. And then we have the correction or the corrective part. Okay, let me add the two elements. This must be plus m multiply x1 derivative dot dot to compensate this. And this is, I put it, but I have to put this. Where I write now? Here. Plus k multiply m multiply x2 desired. This means, let me, yeah, excuse me for the error. The equivalent part include also this part here and this part here, because you have to compensate also this one. It seems to be correct now. Plus the corrective part or the switching part. Again, without this, I guarantee that once I have on the surface, I will remain there. Thanks to this choice of the sliding with the differential equation with order one, because we have two states. Let me see, roughly speaking, the sense here. And the relative degrees between x1 and f is 1. This means if I do the derivative of x1, excuse me, the relative degree between x1 and f is 2. Is 2. In this sense, let me clarify this, because sometimes I speaking without looking. Between x2 and f is 1, the relative degree. x2. Because if I do the derivative of x2 once, I have f of t directly, let me say, in the equation. But with respect to x1, the relative degree between x1 and f is 2, because I have to do twice the derivative of x1 to obtain f of t. This means, as I told you, the derivative or the relative degree, the degree of S is 1, because we have n number of states, if you want, or the relative degrees of x1 with respect to f minus 1. But it's intuitive to see how many derivative I need when I have S dot to obtain f inside in order to control the system. Let me say so. Then V derivative as before, this is a trick which works always mathematically, remain just inside this eta multiplies S of t, inside remain eta minus eta multiply SGN. If I substitute this here, because everything will be cancelled, but remain this without m, because I will cancel here. Of course, if I consider V derivative, I have this expression. Minus eta multiply S of t SGN. This is always the same. It's easy to remember. It's always the same. Equals minus eta multiply the absolute value of S of t. If eta is positive, this is negative. We achieve the goal. Forget this. Please pay attention. We'll re-upload again. Forget this part here, because it was in the problem for in the master thesis. No problem. The problem here of the disturbance, which can represent a bump, even though the effect of the bump is considered directly on the mass, not so realistic in this sense. But let me redo this calculation. This is always the same. We can see if D is at the level, if D is at the level of f of t, this means if D and f, they have the same relative degree with respect to x1, the calculation we have already seen. We've already seen the calculations. This does not change anything. Do you remember? We have seen in another form. You remember, I consider here the maximal value of D, but you can consider also eta larger than the maximal value of D. It's the same. Do you remember? Yeah, I put the maximal value here, and then I consider eta larger than the maximal value of D. Yes, basically the same. You can do in this form here, you can do, as I told you before, very important to understand that eta must overcome the sum of disturbance 1 plus the sum of disturbance 2 plus the sum of disturbance 3 and so on. Of course, it's conservative, but it works. Here, to show this, I use another method, but the idea is always the same. If the disturbance, the bump is 0,20 cosine of 2t, eta is must be larger than this one. And yet the demonstration is done in different form, but basically is the same. Let me consider. I think I didn't forget anything. Of course, it's conservative, but about the conservativeness, if I sum each element in absolute value, excuse me, the maximal value, is nevertheless is what we can do considering a sufficient condition. Okay. I think we can implement, but before implementing, let me clarify one thing which I told you very quickly, but nevertheless important. You remember, basically, we have, in this case, f of t equals f equivalent of t plus f corrective or switching. Now, with the corresponding sign here, the corrective part, if you remember, is a minus m multiply eta multiply sgn of s of t. Now, if I add here minus, typically we consider lambda, multiply m, it does not matter if I don't multiply m, but so we have a direct, this element here, multiply s of t. If I add this element here, I will add an element which helps to reach as soon as possible the s equals 0. Why that? Because this element here is not sensible with respect to the distance to s of t equals 0. Because I multiply by, oh, let me look here better. No, but let me look here, this doesn't matter. I multiply by eta multiply m independently of s of t. Very important that the sign is positive s of t, doesn't matter how big. I multiply by eta multiply m. If s of t is very small, nevertheless I multiply by eta multiply m. I would like to say it's not efficient, this part here. Or probably the best way to express what I want to do does not depend this contribution with respect to s of t. What we add very often, and this part here, because this part here is sensible with respect to the distance of s of t of 0. I mean, the s of t is very large. We have a very large f contribution. If s of t is small, we have a small contribution. For the demonstration of Lyapunov, we don't have problem because, look, because of the presence of this s of t, I will multiply this element here by s of t. This means we have an s squared. If lambda is positive, no problems. To obtain, let me say, the stability. Moreover, nevertheless, we cannot avoid to have this one because close to S of t equals 0, otherwise we don't have, let me say, an effort which is enough to work against possible bumps. I mean, this concept here remains because if I have a disturbance, this element here generate basically oscillation, so large oscillation around S equals 0. Because the idea is to overcome the disturbance. This is not able to do because this lambda here is weighted by S of t. I mean, for S of t 0, or almost 0, lambda cannot overcome a large inputs, disturbance inputs in this sense. Very often we add this one to reduce the reaching phase. Why that? Reaching phase, you remember in the first lecture, is the phase which I try to achieve S equals 0. Very important as soon as possible. This can help because it's sensible with the distance of S to 0, right? Exactly the value of S of t. Reducing S of t, the contribution of this will be reduced. But not the contribution here. Of course, what we did also in my group to calculate this eta of the corrective part additively. Of course, eta small close to S of t equals 0. Let me see if I forgot to say something. Otherwise, we can start with the simulation, I think. I think that we can start with the simulation. Let me come back here to see if I can say something more. Mhm. I think here, no problems. You could add probably not the to understand a little bit better one considerations or two consideration about the choice of S of t. Yeah, k, as I told you, must be positive. The reason is we can see from here, because if it's negative, this differential equation, when S is equal 0, is not stable. The dynamics of the error, this is the error derivative plus k multiplied error. If k is not positive, we don't have the convergence. We can test also in the, or you can test at home, as is easy to see, positive. But which kind of influences in the dynamics? We have seen that eta influence the convergence, no? Because we can see here much larger eta, more negative this. Do you remember more negative? This means basically more and more the concavity of the function, no? Because the derivative of v represents uh, how the slope of this function here, this quadratic function, with respect to the axis is an odd function, no? It's symmetric. This means faster and faster convergent to zero. Please pay attention. It could be that I oscillate around here. But in any case, I will reach this point here quickly. What about k? Cannot be negative as eta, because otherwise the derivative is not negative. About this, probably I have something to show you, but I don't remember if I showed you last time. In the meantime, I insist on the basic concept. No, let me see. I don't remember if I already told you about it. Let me look. Yeah, I could before showing you this, let me conclude with k because it's easy. Then we will insist on the concept of the derivative of v with respect to t, and then we simulate. K is positive. But which kind of effect I have k on the dynamics? I have seen that eta increase the speed, but of course, increasing the speed as always, we can is intuitive. We can speed also. We can also increase the oscillations around the equilibrium point or the goal. Let me say the goal. Do you remember also before we have seen before eta large, eta very large, we increase the oscillations around the goal. The goal was exactly on the surface because we had a system with just one state. Here a little bit more complicated, we will see during the simulations. What about K? Large K, we can see from here. As also in this case, we speed up K, we speed up the convergence. This means also generating oscillations because we increase the input. Basically, it's the same effect as eta. Eta we can see also from the shape of V, but in any case, we can see also from here. But the same effect as K. Oscillation of what? Around S equals 0. As before. You remember here. S equals 0. We say chattering. Chattering. You have to find an equilibrium, an optimal point, an optimal dimension of eta and k. Typically, we do this additively, as I told you before, and then we try to find an optimal k. Because here, we obtained, remember my first lecture, and a good enough convergence even though in infinite time. But increasing k, we are going faster and faster to the goal, but we obtain a chattering problem because we oscillate around s equals 0. Do you remember the chattering? If I want, I show you uh, again let me see if I find quickly the lecture. Let me, 1 second. Mhm. Yeah. Okay, let me see. Dynamical system. Yeah. Oh, but I think I put it here where I don't find now. It's difficult for me to find the material because I don't remember where I put it. Excuse me, I have so many material. So many slides. Hmm. Ah, okay, let me see. Okay, probably I found it. You remember this? Where is? Okay, let me share. You have this lecture here. No? Let me share very quickly in order to be clear what I intend. No. Look, here's the problem. Increasing eta, increasing k. Now we will chat here around. Stronger and stronger. If I increase eta and k. I already discussed you. Even though I am going toward 0, but infinite time. No? In the example as before, the surface was the error. This means once I achieve the surface, I achieve the goal. This means I oscillate directly on the goal. Because if the relative degree is one, the surface or the error represents basically directly the goal. The goal is error equals 0 if the surface is the error, because the relative grid is 1, it's not 2. The surface represents directly the goal, and I oscillate around the goal. Here we oscillate around the surface. Okay, the last things that we take 10 minutes, and then we will come back and we implement the exam exercise on the slide. Let me come back here, just to show you something related to this point here. A little bit to go a little bit in depth. Look at this. The derivative of v and positive function. Doesn't matter how we can choose, but of course, we already seen an idea. For the choice of the surface. It's a differential equation, order, a linear differential equation, to be precise, a linear differential equation with order n-1, which n is the relative degrees which I want to consider with respect to the input, or if you want the relative degrees is the best way to, with respect to the variable which I want to control and the input. With respect to the variable which I want to control and the input. Let me go in depth here, and then I told you another thing. Derivative of this can be written in this form. The derivative of v respect to s multiply the derivative of s respect to t. Must be less than 0. Now, if this is positive, this means if you look at this picture here, we are in this part. No? You are better than me in math. No? If this is positive, we are in this part. Then this means that the derivative of s with respect to the time is negative. If we are in this part here, then the derivative of s of t is larger than 0, such that we have always a convergence. And let me show you a little bit better, if I am able to do, using explaining what I am already told you with this scheme here. At point 0, it's 0 because the derivative of v with respect to s is 0. You remember this concept here again, as I told you before. But let me explain what I told you until now, using these two schemes. I mean, in this part here, if I'm going up, this means the derivative of v with respect to s is positive, then I am breaking. And then I will come back. The reason is because, possible to say, because s of t will decrease. Again, if this is negative, this means I have a region with this is negative. We can see, let me see if I'm able to show you. In this form, let me see if I can explain better. Yeah, I think it's assuming that it's negative, and I have in this positive part, this must be, excuse me, assuming that is positive, negative, again, negative. If I am in this part here, This derivative is positive, but this is negative because this is less. This means that less than zero. This means I am breaking this path. I'm going this direction. The same consideration can be done here. Also here, I am breaking. If I am in this region. Yeah, I am reducing S of t in this direction. Yeah, I'm reducing, let me say, S of t in this direction. I don't know if I can help a little bit to understand V of S as a function of S. At this moment, I didn't put directly this. I mean, I put it at the beginning, but now we can understand better if this is less than zero, that we have basically such kind of function with a slope, large slope. Let me see what I forgot to say. Probably. Let me see. Probably I can add to say something. Look at this. Assuming that I want to control just x2. You remember I told you that the Lyapunov function must consist of all states. But let me consider that I don't want to control x1, the position. This means the relative degree, let me say, of x2 with respect to f, or vice versa, f of t with respect to x2, is just 1. This means in this case, I can consider this kind of function. In which S is this. It is enough to do the derivative once to put S equals 0 using an F, because the derivative degree is 1. But of course, what I cannot control is x1. Could be useful this sometimes. I think next time I will start very quickly. Today I would like to show the simulation. Sometimes it's useful to work with this kind of system. I don't know if you know the Segway, which we want to control the velocity independent of the position. I mean, the Segway should run, the position should be increased. The goal is to control the velocity. I mean, I control the velocity, but the position is free. We will increase indefinitely because you have to run. Okay, let me take 7 minutes. We will come back half past. So we have more or less half hour to implement the system here. I uploaded my site. This could be a very easy but effective example for the question related to the sliding mode control. We are able at the end of today to answer the question of the classical controllers, at least in this selection. And then with this lecture on sliding mode control, we are able to solve some important problems in sliding mode control. And then if you told me that the last lecture is the 2 of June. Now I have to look if I can include something more in the sliding, or at least theoretically, in order to understand better, or to start with the discrete systems to converge on the model predictive control. Let me see. This means if really is the 2 of June, the 2nd of June, excuse me, we have just 3 lectures. I'm not sure. In my, I will check. I will check when. But if you told me, you you know better than me, because in mind I had a little bit longer. But I have to know. Therefore, I ask today because I have to look what I have to select again to select important topics in the concepts of automation and the robotics. In any case, MPC, model predictive control. I have to tell you. Okay, we can take, let me say, 5 minutes, and then we will start with the implementation. This is also extremely important. Okay, let me now implement the model and the control law in this half hour, and then I re-upload. I have to re-upload because I discovered some small refuses, errors. And this could be nice. I don't know if it's nice, but it's a useful example for the examination. And this means you can, as for the first part, no? You can download this software, and then to adapt with respect to the question which or the system which I will propose. Okay, let me share MATLAB. So it could be useful because we will do together in this together, and you can follow me in my steps. Sliding example. Let me here generate in a folder. Let me write sliding mechanical example 01. No, that was the lecture was 01. I mean in the PDF. I will go here inside, not presentation. Sliding mechanical. Yeah. Okay, let me quickly implement the system. Simulink. I will look at Simulink. Let me share. Let me nevertheless close everything which is open from the other Simulink, because otherwise we can. Okay. Now, let me show you what I intend to. I have to implement this. Please pay attention, is 0 here. No? Excuse me for the error before. But we re-upload again. Sometimes f of t is equal u, no? In the common general expression, u is the input. In our case, in the fourth, excuse me here. We multiply the field g of x. Yeah, the field in this case, particular case, is in a vector. Let me implement this. How I can implement this? If you want, you can consider this more physical expression. Let me show you quickly. Let me. What I'm doing now? Where is Simulink? Here. No, this is MATLAB. Where is Simulink? Here. Yeah, this means on the library and the common use blocks, in order to go a little bit faster, you can consider 2 integrals. Why 2 integrals? because we have two states, no? Under common use block, for instance, or mathematical, Gibson mathematical block too, no? Here we have x1 position. Here we have x2, because do you remember the derivative of x1 is equal to x2, no? This means the integral of x2 equal to x1. And here we have x2 derivative. Let me write so. Dot x2, just to understand. Now, dot x2
Paulo, hi.
così.
Kannst du uns einen Gefallen tun? Wir haben gerade die Infositzung. Du warst dein letztes Mal Kassenprüfer. Könntest du einmal kurz über die 5 Belege gucken, ob das soweit in Ordnung ist?
Gerade jetzt, gerade in einem Termin, in einem Meeting.
Ah, okay, sonst wie lange wäre
20 Minuten, halbe Stunde maximal.
Ja, okay. Fertig wäre
Franz, wenn ich ab und wie viel Uhr ist, ja, seid fertig?
Wir sind jetzt fast fertig.
Okay. Aber kannst du oben lassen oder muss ich schließen die?
Ja, du müsstest uns einfach drauf gucken. Ich meine, das war alles in Ordnung durch die Buchung.
Für mich ist in Ordnung.
Ja.
Und guck,
Okay.
das bedeutet, wenn du lässt da oben, dann, wenn ich fertig bin,
Ja, alles klar. Dann lege ich für uns einen Zettel rein. Dann, dass du dir was sagt.
ich vertraue.
Ja. Alles klar, danke, Paul.
Ich danke dir.
Ja, ciao.
No, excuse me for this interruption. Let me what is x2 derivative? Is this one, huh? X dot dot. If I divide it by m and I put everything which I have here on the other side, I have exactly x2 derivative. Let me write in MATLAB this. To write this in MATLAB is easy because from common use blocks, from common use block, I can consider this block here. I can write here inside 1 divided m, as I told you, divided by m. And here, what I have here is the sum of all acceleration, excuse me, forces acting on the mass. Because here the acceleration, excuse me. This means here I can consider the sum, again, on common use blocks. Remember, I told you where this is. If you want, I can show once. Here's the most important, let me say, under Simulink, we have this under directory. Common use block, you can find a lot of block, which is really the most used. I consider the sum. I click on the left and drag. Let me now share again. Let me put here inside. Let me consider now a round shape. And then I have it here, I have it 1 plus, 2 plus, and 3 minus. Because we have on the right part f of t, d of t with plus, and then 3 elements which works against. Let me show you what I intend. Plus, everything divided, m, 1, 2, 3, on the other part with minus, everything divided m. Because the idea is to express x2 derivative, which is x dot dot. Okay, now we have here, let me see d of t, the disturbance. Here we have f, which came from our controller. And then we have to realize here the model. But it's not so difficult, basically, because, for instance, here we have Ks multiply x1, the spring effect. This means I copy this, and here inside I write Ks. It's possible, better to put here, better, Here, I have to consider the Coulomb friction. This means I have to consider one element here and the other element here. Now I show you better. This means here I will put, you remember, the name was KF1. Yeah, I will put KF0. Of course, I have to define this element here. And here I have to consider the sign. Now I'll show you a little bit better. The sign, basically, let me show you, this could be useful also for you. Typically, is the math operations. Yeah, sign. This means sign of the derivative, of the velocity, multiply kf1. Of course, this could generate some problems in the calculation. If yes, multiple crossing point, we have to fix, or fix means the system itself will approximate. Let me share, because I didn't share probably. Let me, sometimes I forget. Where is? I click on the left and I drag. If this generates some problems, multiple crossing point, I have to fix. This means the system will approximate itself, or we generate an approximation with remember, this sigmoid function, hyperbolic tangent, for instance. Okay. Yeah, I think I didn't forget anything. Let me realize the controller. Let me go here. Okay, here. What I realize is x2 derivative equals f of t plus d of t minus this, minus this, minus this, everything divided by m. Now, concluding, and then we will test together. Mathematically, I show you that this control law, including an f, this control law includes an equivalent force. Until here, I forgot at the beginning, this part here. I will scan again, I will send you exactly now. Plus the corrective part realizes our control law, which basically allows to achieve in finite time st equals 0, allows to S equals 0 means this dynamics here. This means the error between what I want to obtain in terms of x1, what I want to obtain, excuse me, the error in terms of x1 is going asymptotically to 0. Of course, x2 is fixed. By what? By the system. Because if I fix the goal for x1, x2 is the derivative of x1. Of x2 is the derivative of x1. I cannot change. Therefore, we're speaking about the relative degree of x1 related to f, or vice versa, f related to x1. Yeah. And if eta is large enough, remember I told you a lot. If eta is large enough, larger than the maximal errors, let me say, we can realize in the controller, which is not the controller, the controlled system is not sensible with respect to any kind of disturbance. Let me implement this and then we will test. I copy now in Simulink this control strategy, which came from our calculations. Yeah, I will realize here. At home, please try to include this in substitute. I can do that later. Okay, this means sum of what? Control invert, I can invert the block, no? Control I. We have here, let me show you so we can understand better. 1 plus, 2 plus, 3 plus, 4 plus, 5 plus, 6 plus, and 1 minus. You didn't see. 1, 2, 3, 4, 5, 6 element with plus and 1 with minus. 6 element. Two, 3, 4, 5, 6, and 1 with minus. I hope no mistakes. Try to do at home if I don't think so. That there are mistakes. Okay. This means here I copy kf1 multiply x2. X2 is here. You can see now. Okay, but I am copying from the kf0 from the math, no? Multiply sgn of x2. Ks x1. Exactly. Right. Then m multiply k x2. K is in the design element. You remember I told you also the meaning. Multiply x2. This means here. This means here inside I have to write m multiply k. Then we have m multiply x1 desired, twice derivative. This means we have to consider here. Ooh. M multiply x2 derivative. X1 derivative, excuse me. Let me write here to remember no? What we have to do. Desired, excuse me. Desired. And copy from our calculation. And then we have a k multiply mx2 desired. I hope no mistake. No? Not so because sometimes I don't want to say it's complicated, but it's a little bit boring. This means here is x2 desired. And the last one is the corrective part. Eta m sgn multiply s of t. This must be defined. Here, instead of k, I have to put eta. Here I have to define s of t. I hope no mistakes. Okay. So sometimes I don't see well. Okay, define please s of t. S of t was the error. The dynamics of the error of x1. This means we have here the sum of two elements. Let me say plus minus, plus minus, plus minus. Which we had. I copy from was x2 minus x2 desired, x2 minus x2 desired, yeah. At home, try to do a little bit better, no? And then here we have plus k x1 minus x1 desired. This means it's not so extremely suitable. This let me do in this form. I copy this now. This is x1 is a little bit an exercise. X1 minus x1 desired, which I don't have here. No? It's the first time that we are using x1 desired. Yeah, right. Then we need a block plus plus. And here in the middle, we need a k, no? The middle in the sense, yeah. Let me save. With the name make x01 simulate. Now let me define an M file with all this data. This means let me come back. Where is? Oh, unbelievable. What I did until now was this. Now let me go here. Let me open a new file and let me define data for the mechanical example 01. Huh? What I need? I need k, I don't know, equal 10. Larger in the values means very fast convergence, but risk of oscillation around s equals 0. Then we have m, the mass, 30 kilogram. Then we have kf0, 20. kf1, 35. Typically, this is a little bit larger, 50. Take 60 is okay. Then what we have? KS 200. Then we have eta. Let me see, very large, just to start. I think we have everything now, more or less. Let me see. If I forgot something, we can, let me save. Like data make example 01. Let me run. If I forgot something, we can see later. We can see here the data. Now let me come back to Simulink. Just to test is enough to here. Yeah, x1 desired. Let me put in a constant just to see, and then at home you can check whatever you want. Under sources, please remember, under sources, we can find, for instance, a constant. I don't know, 1 meter. Makes sense too. This means this signal here, which is the desired x2, if you remember that x2 is the derivative of x1, this means it's 0. This means the derivative of 1 is 0. This means the second derivative is also 0 here of x1 because it's in constant. Let me see if I forgot something, then we will see what happens. Yeah, okay. I see eta. I wrote here capitalized. This means let me write here eta. Let me look what happens. Yeah, we have this zero crossing. Let me fix. Let me see what happens. Mhm. Zero crossing means the system approximates itself, this SGN. Do you remember? SGN numerically could generate problems. No? Okay, let me stop. Let me put some diagnostic, some scope. The scope are under things. Let me show you this at least. A few minutes. Scope, did you see? Click on the left and drag. Let me go here again. Look here. What we want to calculate, for instance, let me take under sinks. Under sinks. No, I think it's under senior routing. Under senior routing, please remember this max. The goal x1 and x1 desired. Of course, yes, I put it in a constant, but you can put in a sine, cosine, because also constant is not so nice. A little bit oscillation could be nice. Let me see what happens. And of course, if you put sine, cosine, you have to consider uh, here the second derivative of sine, and here the first derivative of sine, because it's the x2 desired. Please pay attention to this. Here we need the first derivative of x1 desired, because we are x2 desired. And here we have the second derivative of x1 desired. I mean, if we don't have a constant, you have to be careful. Let me see what happens. It should work, I hope. No, let me show you. Somehow, let me show you how I can share now. It's not so nice, but now we have a small bias, which I don't understand. But as first attempt is not so bad. Too large this bias, my opinion. Let me see why we have this bias. Should converge to one. Oh, problems. Okay, let me analyze. Let me short the simulation time. Let me put 1. Let me analyze the S. S should be 0. S is here. No? Let me comment here a little bit. It's there. No? No, it's not there. Oh, it's there. No, it's not there. There's there. Okay, it's here. Put a little bit larger this. Why S is not 0? It's interesting. I show you. Okay, it seems to me that we need a little bit larger eta. Let me put it here. Or better in the M file. Let me show you. It could be that we have numerical errors in the or an error in a physical error in the implementation, physical in the sense I put something wrong. Let me show you now again. So slow. And now is the simulation extremely slow because I have an big parameter numerically. I know why, probably because we approximate SGN no, internally. This could be a problem always. This means let me share now. If we are not able to get the results, we have to approximate with hyperbolic tangent. No? This it could happen. It could happen that now it's so slow because of numerical reasons. Because we consider really a very big. Okay, let me stop because it's too slow. Let me reduce a little bit. Remain here. No? Let me reduce a little bit eta. I didn't share it, but let me reduce. Let me now simulate again without sharing. No? Let's a little bit more acceptable the time. But if you don't reduce in a significant form, we have to consider to approximate SGN with this hyperbolic tangent because or tangent because internally if they realize and it seems to be as before more or less they put an hysteresis inside. I don't like this. No, it's not acceptable. Let me show you what we can do. Okay, instead of this, let me copy close to here. Let me put here an hyperbolic tangent. We had no hyperbolic now. To find again is not so easy. Let me see. In math operation was no math operation, I think. What, I don't remember where. Oh, in math operation, I don't see it. No, it's not here. Why? I don't find it. Okay, if I don't find, let me see. Let me go under user defined function. Let me take this block. Let me see if I'm able to use it. Control invert. Let me see if I am able to use it. And here I will put, I don't know, 100. I hope that it works, but I'm not sure. Because typically I work with a different. It seems to, at least it's running. Let me see what I am doing. Now, you can see what's the problem where, no? The problem was that the simile approximate with an hysteresis inside. No? generated in a region in which, yeah, that zero does not exist at all, no, in the sense. Yeah, zero is the resolution of the machines. The last, and then I will close this part, but I think it's interesting. No? I will upload this. No? Look what I am doing now. A disturbance. Let me consider disturbance. Let me share here. I found here this important function, MATLAB function, under use defined function in order to build some particular math functions if under math operation is not there. Look here, under sources, let me consider the bumps. Bumps. Where is the bumps? You can consider any kind of signal, random signal, noise, but let's consider sign. Click on the left and drag. Yeah. You can place here with the amplitude, with the frequency. Very important, eta larger than the maximal amplitude. Of course, it's conservative. We need probably less, but look what happens. Let me share what I did. Again, eta larger than the maximal values, which we have here. I didn't check inside. This is the results. But of course, probably the amplitude is very small. Because eta, in our case, let me share, is extremely large. Let me reduce this. Then I run. Let me come back here. Here we have an amplitude 1. Let me share. This means should be compensated. 10 is larger than 1. Let me show. Ah. Let me see. Yeah. I don't understand why it does not work. 1 second. This is the result. But I use 100. I don't understand why with 10 did not work. Let me see the calculation 1 second. Or let me see here before. Let me see the calculation. It could be that we have an error. No, I don't think so. Oh, let me see once again. Oh, I don't understand why. It could be that I made mistakes in the implementation here. Please check because check again the calculations. Strange. I don't see any errors. Should work also from much smaller. I mean, if the amplitude is one until one, let me say so, should work. But it could be that during the implementation, I make some mistakes. Okay, let me increase a little bit the approximation here. 1 second, and I try to clarify why if I put 10 in eta does not work, should work. Let me see. No, 1 second. Where is Simulink now? I don't understand really. MATLAB. Oh, why is Simulink not visible in Zoom now? I don't see Simulink anymore. Stupid situation now. Why Simulink is not visible? Now, okay. Let me see what happens. Approximating better SGN. There is an error because reducing eta does not work, but it should work theoretically. It could be that I have an error somewhere. Just this moment, I don't see it. Or we have an error in the we have an error in the cancellations. Could be also this one. But in any case, look what happens. This nevertheless must be a little bit clarified. Increasing eta. It could be that we have an error in the numerical error in the cancellation. It seems to be a little bit too strong or too large, this error, but it could be. Look, and then I will conclude. The result which I have, but it could be that I made the mistakes or some mistakes in the calculation, but in any case, we can see or in the implementation that the sliding mode control is able to obtain despite the bumps and errors, the level which I want to obtain. I mean, let me show you what is going inside. This is the bumps. We can increment also the frequency. Let me show. I incremented the frequency. Let me show. Okay, this is the bumps, which we have in 1 second. The result is always the same because we have seen, let me show, that the result adjust depending of the amplitude. No, we have to overcome the amplitude. Now, I don't know why, where is the error, but could be also the cancellation error. The reason is it seems to be too large, this cancellation error. The reason is that here I didn't put SGN, but an approximation. Excuse me. No. Here the cancellation is not here. The cancellation is here. This means the cancellation should be perfecto, almost perfect. Okay, let me do another attempt. Yeah, it seems to be everything correct. Try to do at home. No, try to do at home. In any case, is it possible to compensate? It could be that I make some mistakes in the implementation. Now I will upload and try to look what is the check. The amplitude is 1 meter, no? Very big. If eta is larger than 1 meter, should work. This means, of course, we approximate SGN, but in any case, the amplitude of the oscillation should be reduced. Now we can see this is totally reduced, but of course we are considering eta equal 100. It's okay, but should work until 1, larger than 1. But it could be that during the implementation, could be, oh, I made some mistakes in the calculation. This means we have an error, not only the disturbance, but also an error. Numerically, should be the error relatively small because the equivalent part is exactly the model, no, with SGN. Okay, if you have questions, I'm here. Otherwise, please check for, if you have a question, could you explain why there is an K in the equation for S and what was meant by the degrees of the sliding variable and other equations? Yeah. K is there because, let me go to the lateral camera. The problem is connected with the relative degrees, of course. The reason is, if you look at this equation here, I don't know if you remember the first lecture, the first slide, which I introduced last time, in which, do you remember, one variable was in a linear combination of the other one. Let me open the lecture, probably can help. Because this lecture at the beginning isn't a fundamental lecture, even though now, of course, it's difficult to remember because first time when you hear about this, is difficult to have in mind everything. Yeah, do you remember this example? This example is exactly our example. To state exactly, no, because it seems to be more complicated in our case. But look at this. The derivative of x1 is equal to x2. We have also. Then we have the derivative of x2 equal u. Of course, in our case, we have here a lot of things together with u. But what was the idea? The idea was, if x2 is equal minus c1 multiply x1, remember this. Let me. I can consider now this equation here. Why that? Because if x2 is equal minus c1 x1, I can plug in here. And now I can solve this. Easy, no? Do you remember last time? And if I can solve this, the solution, this one, I can solve also with respect to x2, because if this is x1, c time x1 is also basically the same solution multiply x1, c1. But this is the problem here in this case. The problem is, does this possible position is not really feasible, because exactly in our case, this means the velocity is proportional to the position. This is not really possible to realize. But look at this. Including this relation in a more large relation, in which s of t is a variable sliding, which include the combination x2 and c1. Now I can indirectly, not physically, realize x2 equals minus c1 x1, considering now another problem to converge at s equals 0. This is done inside the microcontroller. Is in a way, virtual way, to generate x2 equals minus c1 x1. Not physically with a sensor or controller, but just in software form. Now, in our case, it's exactly the same here. You remember, at the beginning here, the idea was to steer, to control the system to 0. You remember here. I have these initial conditions, and the problem is always the same, to steer the state to 0. In our case, our 0 is our desired position. Could be 1 meter, could be 2 meters, could be in a slow and comfortable oscillations, and sine could function. This means here we have x2 minus x2 desired plus k, or the c1. Our case is the old c1 multiply x1 minus x2 x1 desired. What is it? Is this? If I was able to present last time this nice example, now it seems to be clear. Yeah, at that time we have x2 desired 0, x1 desired 0. Now we have a different 0, because 0 is just an abstract concept. Mateusz, I don't know. Mateusz said you explain it. This now is no need. Mateusz, I confused you. I don't know.
No, sorry, because I asked before and you explain after this, and now there is no need. But if you want, you can explain, because sliding variable, there is need for that, because that you said that physically we can't in two-state system we can't do proportionality, and this is because for offset that we must direct steer sliding variable, because if we steer x2 which is the derivative of x1, this will be steer indirect, and this is main meaning of sliding variable.
Yeah, everything is okay. But now I think reconnected my original introduction. Now we can understand probably a little bit better the meaning, what I did last time with this easy introduction. And now we can see exactly that this is here. If you look, this was 0, this was 0. This expression here is exactly the same, but considering the system. Very important now, does S equal 0? Or we consider indirectly that the position, the velocity is proportional of the position. Why that? Because we realize this concept inside the microcontroller. Show you this and then we conclude. I will show you this. Look, What is S? Is here, but S is inside the microcontroller. Basically, the microcontroller consider this part here, or this signal here, everything which is, let me show you. Too much. From here, everything is from here is realized in the microcontroller. The signal which come out is basically to realize using electronics components. To be precise, I have to include this element here. If you want, I do it in a sum, and the output of the sum is the signal to be realized by the electronics component. If you want, I can do this, and this. In order to understand that S of t equals 0, which realize indirectly x2 equals minus k in our case, multiply x1, is a virtual equation inside the microcontroller. This is an extremely important concept. Let me write here plus minus. No? In order to look what is in the microcontroller, plus 2 times plus and 1 minus, right? Something like that. And here I need just 1 plus at the end. Yeah. Extremely important concept. But S of t is something inside the microcontroller. With this signal here must be realized practically using electronic components. But S of t equals 0, which realize in a virtual form our proportionality between x2 and x1 is inside the microcontroller. I forgot here something. Yeah, okay, because this is 0. No? This means I have to put another plus, right? Yeah, because this belongs to the control law. And K states basically K state basically the speed of the convergence on the surface. One second. Let me see if I connect everything correctly so that I can upload the material. Yeah, it's still working. But I am a little bit in doubts about the parameters and so on. And K, of course, increasing K, it could happen that we end up in oscillation. This I told you because we increase the input actions in this as eta, as eta. Okay, Mateus, thank you for your question. We can come back next week, but I think that if really you have to conclude the lecture the 2nd of June, I have to move another selected topic, discrete control MPC. But it could be that we show you something I flesh out for your knowledge, something related to the Segway, which I already presented in the lab. I don't know if you attended the class of the lab, but can be outside the program of the exam in order to understand better the importance of the sliding mode control. Okay, thank you for your active participation. If you have other questions, I am here. Otherwise, next week at the same time. But check really if the 2nd June, in mind, I have 1 lecture more, at least. But if it's 2nd June, no problem. In any case, I have to tell you about the model predictive control, because in a selected, really fundamental topic in automation, in any case, robotics too. Probably you didn't hear about model predictive control until now. Therefore, this is important to hear. Sliding, probably you heard about, but okay. Thank you. Bye.
Thank you very much. Goodbye.
Thank you, Mateus, for your active participation. Thank you to everybody.